Hello and welcome to this last lecture on purification and separation methodologies. In today's lecture, we are going to study high performance liquid chromatography, which is an advanced form of chromatographic separation method. In this lecture, we are going to discuss history of HPLC, which is high performance liquid chromatography. We will discuss and introduce the instrument. We will delve upon the theory of HPLC, and towards the later end we would discuss the instruments and the nitty-gritties of the instrument. So, what is HPLC? It is an evolutionary equipment for separation. In the last lecture we discussed about gas chromatographic instrument GC, and we realized to what levels it is advanced from the normal chromatographic techniques and instruments we have been using. HPLC, as the name suggests, it is high performance liquid chromatography, has evolved after GC came into being and got established, which was by the time around 1960s or so. So, from 1960s onwards, there was a need felt to develop a new methodology which was simpler than gas chromatography GC, but nevertheless would encompass all the good things and positive attributes of the GC, and that is how this methodology got to a start. So, in the last 35 years this has been still going strong and has now become as the largest separation method used in chromatography. So, as I said about the history, in 1960s, the time when it started to come, it was known as high pressure liquid chromatography. Now, at this point I want you to keep in mind two factors. The first is, for any liquid chromatography, if you want to attain, for example, extremely high resolutions, and also all those resolutions of solutes would be attained in a minimum time, what would be the requirements? At this juncture, we have come to a point where all of you know about capacity factors, resolutions, and the Van der Mertier equations. So, based upon that knowledge, what are the things which could be done? There are two things. To elute the mobile phase within a very small time frame, we can apply pressures, right? But the one big limitation with applying huge pressures would be that you would never be able to retain a very good separation, right? So, to enhance separation, what needs to be done? We would certainly need to evolve certain highly sophisticated columns, right? And then what I mean by columns is to evolve some very sophisticated stationary phase in chromatography, and that would pave way for development of a method such as HPLC. So, then in the late 70s, as far as based upon all the modifications done in stationary phase and also the methods and the instruments came in, this method has started to be known as high performance liquid chromatography. And there had been so many other synonyms used for this method which have come in the recent past, such as UPLC, RRLC, UFLC, RSLC, etc. For example, UPLC stands for ultra pressurized liquid chromatography. So, there are these three questions which we had been asking whenever we were discussing chromatographic methodologies. What is this HPLC? When would you use HPLC and why is there a need for HPLC? Something which I have already spoken about a little bit, right. So, the first question first, what is HPLC? It is a form of advanced liquid chromatography, and I would make an amendment here. It is a form of advanced liquid chromatography in general that separates the mixture of analytes which are dissolved in a solution within a very small time frame and under high pressures. It is a very powerful tool of analysis which yields high performance and high speed compared to traditional column chromatographies because of high pressure generating pump operations. But as I have mentioned previously, it is not because of evolution of such high pressure pumps which had revolutionized this method. It is primarily the kind of stationary phase which came into being at the later end of this 1950s or 60s. Something which allowed chromatographers to use the number of theoretical plates which were just like equal to 50,000 to 60,000 or more per meter of such columns. So, such was the efficiency of this chromatographic method. The second question, which is when would you use HPLC? So, HPLC can be used for both analytical purposes and it can also be used for preparative purposes. When we say analytical purposes, it means we are only interested to determine chemical composition of a mixture, right? And whereas for preparative purposes, we tend to actually isolate the substance. So, it caters to purification of a substance out of a complex mixture. It also can be used for both qualitative and quantitative purposes. Now, what do we mean by qualitative and quantitative purposes? You remember a typical chromatogram, right, which mentions about a typical retention time TR for a given peak that we had seen in the previous lectures. Now, if a chromatographer is able to maintain all the conditions of a chromatographic experiment constant in HPLC, right, which means that the stationary phase used should be the same, the type of mobile phases used should be the same, the pressure generated should be the same, all the conditions remaining same. Under that particular set of conditions, your solute should always get eluted out with the same retention time. It means here we have generated a new morphological signature feature for a particular component, which is its retention time, right. So, this is what we mean by qualitative analysis. With quantitative analysis, it means in a given sample, we would be able to determine or approximate concentration of an individual component using HPLC, using a typical chromatograph, and that can be done once you know the peak height and you calculate peak area accordingly, right. Now, the third question, why? And I think I delved on this question a little bit in the previous slides. There was a need felt after GC was completely established. There are certain things which one cannot attain with GC, things which can be easily done with HPLC. Let me just show you. Number one, HPLC is a method which is not limited by sample volatility or thermal stability. Remember, in GC you need to have a sample which is volatile and which is thermally stable, right. This is not required in HPLC. In GC, if you could remember, there are these two interacting phases which really do not exist, because gases as mobile phases are not going to interact or react with the stationary phase. So, we need a more orthodox method in which there is interaction between a mobile and a stationary phase, and HPLC provided you the right answer. Room temperature analysis in HPLC, we have a temperature modulator. You can increase the temperature, but then those increase in temperatures are quite mild. So, you just warm the column and not really heat the column as you do in GC. Ease of sample recovery. So, you know what happens in gas chromatography, you cannot recover your sample, whereas in HPLC, in preparative I have already told you that the samples are in fact isolated. Now, coming to the most important components of an HPLC are the following: a solvent reservoir, it got to have a pump, it should have a sample injector, and of course a column, and finally a detector which would be providing you the analysis in the form of a chromatogram. Let us look at this in another way in an instrumental diagram. So, if you look at this instrumental diagram, you see these mobile phase reservoirs, which contains generally can contain up to 4 different mobile phases or solvents, and then you have a proportionating valve, which means you can modulate of which concentration you want these mobile systems or solvent systems to come out of this mobile reservoir. Then it leads up to the pump, and we will soon know about the kind of pumps used in HPLC. If you use, which is generally used as a reciprocating pump, if one is using a reciprocating pump, one would require what is called a pulse dampener, which leads to a loop injector or an injector, and then it guides finally to a guard column and to a main column, which then finally ends in a detector. So, these are the primary components of an HPLC. We will look at these components in a bit more detail. This is an image of an HPLC. So, one can easily see a mobile reservoir here. It contains those 4 bottles. I think a couple of them are not visible. Then below this mobile phase reservoir is a degasser. I will come to this part in the next slides. Then below this degasser is a pump here, and then this is a very sophisticated modern age HPLC. So, it contains an auto sampler. One may or may not opt for an auto sampler, and then there is a column thermostat and a detector, and finally the analysis is done on a computer screen. So, we look at the parts, the components of an HPLC in a bit more detail. So, let us first discuss the mobile phase. We know by now what are the characteristics required for a mobile phase in any chromatographic experiment. It should be affordable, it should be non-hazardous, it should be inert, and the sample components should be miscible with it. Detector should not respond to mobile phase, of course, and there is one more thing which I would add, that your mobile phase should also not dissolve the stationary phase if that stationary phase is a liquid. So, that is in addition to the points laid out here. Coming to the stationary phase used in HPLC, and I would like to spend some time here. What happens generally is we tend to use stationary films rather than stationary solid particles, and we use films. The reason is we tend to minimize that C term in a Van Demeter equation. So, that would eventually lead to higher number of theoretical plates, right. Now, what generally happens is you have those very small microporous silica particles, which are then coated with this liquid film. Now, because you are using very high pressures, so those liquid system, that liquid stationary phase can actually sometimes be drifted away using those high pressures, and that is something we call as bleeding in a column. To prevent that bleeding, what we do is these stationary films, rather than being physically attached to the walls or to the surface, are actually covalently reacted to the surface. For example, silane particles are reacted with this kind of silica molecules on the surface, and they tend to provide this SiO-Si bond, which is quite inert, which is going to stay there and would remain unaffected by high pressures, right. So, you have this R group which can be modulated in a column. In a normal phase column, this R group can be very polar. It can be a group like cyano, it can be a group like a diol, it can be an amino group. Whereas, in a reverse phase column, and this is the column which is most widely used in HPLC, in which R remains non-polar, a group like C8 or C18, right. Now, one more thing, out of all the these kind of siloxane molecules, SiOH molecules, not all are reacted with these kind of silane molecules. Almost half of them or approximately half of them are reacted like that, and another half react with a normal silane with SiCH3 thrice. So, it means those OH groups are completely sealed, and we call such groups as end-capped. So, 50% of the molecules, 50% of the residues would be end-capped and 50% of the residues would be functionalized in an HPLC. That is how the stationary phase is built most generally in HPLC. Now, you can use different mobile phases in HPLCs in reverse phase chromatography. I think this point was probably told in the previous lecture. Water remains as a base solvent, right. So, it means it will always be used, and with water one can use methanol, acetonitrile or tetrahydrofuran because they can be used depending upon the kind of polarity one would like to see in a chromatographic experiment. Whereas, in a normal phase one can use hexane, heptane or isooctane generally as mobile phases. Now, these are the things one can change in an HPLC. So, as far as mobile phase is concerned, one can change from a polar mobile phase such as water and can reach up to hexane as a non-polar mobile phase. Stationary systems, one can use silica or those modified bonded phases such as cyano, C8 or C18 as non-polar stationary phases. One can also has a wide choice of solutes which can be run on such systems, right from salts to alcohols to aliphatic or aromatic non-polar systems. Apart from all that we have discussed, there are a few more points which one should keep in mind while using HPLC. We also tend to use certain buffers in order to adjust a pH in a mobile phase system, and that is also generally done. So, that depends upon what kind of solutes are there in your system and whether you want those solutes to interact more with the stationary phase or remain more in the mobile phase. Degassing of solvents. So, that is a very important phenomena. You could recall there was a degasser there in the image I showed you. Degassing is generally done to prevent bubble formation, and those bubbles can come out because of, let us say, some dissolved gases like oxygen or nitrogen present in the mobile phase. And what they do is, once you put them under extreme pressures, they tend to evade out in the form of bubbles, which create unnecessary trouble and certain noises in the system. So, degassing is done either you can use a vacuum and take out the gases, or one can also purge them with helium, and that is how degassing is also done. Washing with water is needed every time one uses a buffer, so that a column is not damaged. Likewise, a guard column, that also you could recall, we saw it in the previous image, is used prior to a column, and that is only used to enhance the column lifetime. A guard column in constitution is similar to a column. The only thing is it is cheaper, it is very small, and it takes all the particulate matter, or for example certain solutes which attach, which adsorb almost irreversibly to the column, and that is how a guard column makes sure that those particulate matters or such solutes do not reach the column. As is understandable, a guard column needs more frequent replacements in comparison to the main column. Coming to the second part of HPLC, which is an injection port. Now, that is something very interesting. We use a sample loop rather than a normal injection as we see in GC, and the reason why we do it is the whole system, mobile system, is running under huge pressures. So, a normal injection cannot be made. Now, the way it is made, you have a injector port which is a 6-port module, and in this 6-port module, if it can retain in 2 positions, one is a load position and another is an inject position. In a load position, once you make an injection, the injection goes to this part, this sample loop. The sample loop may be up to 2 ml. It gets filled with this solute, and then at this time whatever is coming from the pump and going to the column remains completely separate from this sample loop, right. So, after the injection is made, this port is twisted by 30 degrees and we say it has been at the inject mode. And what happens in an inject mode, as soon as you do it, it tends to bypass this injection port, whereas this injection loop becomes a part of this main system. So, now your whatever is coming from the pump is taking the solute in that loop and that is being taken to the column. So, that is about the injection port in HPLC. As far as pumps of HPLC are concerned, they can be constant pressure pumps or pneumatic pumps, they can be syringe type pumps, and the most widely used ones are the reciprocating piston pumps, and that is what we are going to see in a little bit details. So, in a reciprocating piston pump, solvent delivered through reciprocating motion in a hydraulic chamber. Solvent is sucked on the backstroke and delivers in the forward stroke. Now, if this happens, one could easily see that in this motion there is going to be some lag, and what we call is generation of a pulse. So, while a piston is thrusting the liquid in, it is generating huge pressures, but by the time it is taking it out, the pressure, there is a drop in pressure, and that means there is a pulse, right. So, to avoid such pulse, one use a pulse dampener, and that was seen in the previous slides. Okay. A dampener basically just maintains that pressure same. It takes in a more layman sense, it takes the kinetic energy of the piston pump during its flow and uses that kinetic energy when it is in the resting position. These kind of reciprocating pumps are mostly required for gradient operation, and I hope you understand this gradient operation that we have already seen. It means use of more than one mobile phase in different proportions at different point of times, right. So, as I mentioned, temperature control in HPLC is generally not required except in a few cases. So, the cases are, for example, if retention time of each component is temperature dependent. Number 2, if variation in temperature may cause change in peak area or height, and if the compounds are dissolved in higher temperature. So, then the column must be set in a similarly high temperature. But having said that, I would again reiterate, the columns, the kind of temperature we set in HPLC column is nowhere close to the temperature we set in a GC column. So, finally, we come to HPLC detectors. The detectors are based upon the sensitivity, selectivity, adaptability and operability. Based upon that, one can use refractive index detectors or universal detectors, one can use spectroscopic detectors or electrochemical detectors. Most widely used ones are spectroscopic detectors, and even amongst those spectroscopic detectors, the one which is most widely used is diode array detector, which is basically a UV-vis detector which simultaneously can detect different wavelengths. So, what basically happens here is you get a chromatogram which is the absorbance as a function of time, but in this diode array detector your absorbance is not only function of time, but is also function of a wavelength. So, you get a huge wide spectrum of wavelengths. So, at the end what we have seen so far in all the last 9 lectures or so is we started with purification and separation methods, and I told you why various methods of purification and separation from olden times have become more or less obsolete. And there I told you that chromatography is a quantum jump as far as methods of separations are concerned. Thereafter, we built the concept in chromatography, we discussed some basic terms in chromatography and certain classifications in chromatographic systems. We discussed some of the most important concepts in chromatography, which are resolution, selectivity, capacity factor, column efficiency, and based upon that there were two theories, and we discussed those two theories, plate theory and rate theory, and then the rate theory helped us and plate theory established us these equations, Van Demeter equations and other equations. Finally, we got resolution equation, and we found out how to optimize a particular separation in a complex mixture. And then we discussed gas chromatography in details, and we discussed HPLC in today's lecture in details. So, that brings me to the end of this topic, which was purification and separation and chromatography, and I hope at the end of this lecture you were able to take home a lot of new concepts and new ideas, and I hope this have been a fruitful exercise for all of you. Thank you very much. Goodbye.